the driving force for the lattice distortion. And actually, if you think about it, what we're doing then under photoexcitation is we're depopulating these states, which are the very driving force for the monoclinic distortion, and occupying these higher energy states. So it could be that by depopulating these valence band states, we slightly reduce the driving force for the monoclinic distortion. That was great as experimentalists to say, so we asked our theory colleagues, does this make any sense whatsoever? And they said that's a really hard calculation, but they were convinced it was interesting, and they spent about a year doing it. And they did. So what they did is they calculated this is a bit of a complicated diagram, so let's step through it. So under no Doken, in the ground state, what they did is they calculated the energies of 0 here is the tetragonal state, and 1 is the full monoclinic distortion. So this is some sort of a distortion coordinate from tetragonal to monoclinic structure. Their calculation predicts what we expect, that a fully monoclinic structure is what you would expect in the ground state. However, then they added 0.1 holes per unit cell. That corresponds to about the excitation fluence we use experimentally, and they get the red curve. All right, what that's telling us is that under photoexcitation, in the presence of a hole, the ground or the minimum energy state of the system has a much lower monoclinic distortion than the non-photoexcited structure, right? And so, moreover, it's much closer. It's a much lower well. So as you have thermal energy that allows you to sort of populate up here, we're going to have a much lower monoclinic distortion. So this basically is what we believe to be occurring is a photoinduced hole-related driving force for this photoexcited state of the material. Okay.